Okay, so welcome to our presentation. So in here we are recording the videos, and in order to show you guys what we guys been doing all the time. So in here, I would like to briefly introduce what our group is doing currently. So we basically divide our research into two parts. So the first part that we conducted a cross-national study, which means that we basically selected several countries, and also we collected some data, some climate-related data, and also some kind of like country-level statistics. Yeah, and we also like kind of conducted several regression analysis. So in order to research the relation between the climate change and probably the agricultural production. And for the other group, they have conducted domestic study, and their data is basically from China. So later we will have more explanation. And today I am the first presenter representing the cross-national study group, and my name is Gong. And later Yu-san will introduce you guys the other study, which is the domestic one. So let me just start my part. Right. So for the first part, I would like to introduce what kind of data we've been using for this study. So for our study, that we basically use three data sets, and the first one will be is from FAO. Second one, it's from here, is right over here, it's called the OWID, and the last one we get it from the global microdata. So in here, I will just explain you guys like what kind where from which data set that we have garnered which kind of data. So in here, for the first data set from FAO, we basically garnered a lot of different kind of like data according to, for example, in here we have the different types of like crop productions, including apple, bananas, things like that. And we have their production data per year. In here, this is the first part. And later we're going to use the production as the dependent variable, as the dependent variables. So in the second part, it's obviously from the OWID dataset. So in terms of this dataset, we basically get the very key explanatory variable, which is the temperature, as well as the other one is the precipitation. Right. And for the last part, we've been getting a lot of control variables out of this global macro data set. So in here, I can just like show you guys what we have got. For example, a nominal GDP, population, inflation, unemployment, government expenditure, etc. Right. So the next part will be merging all this data all together. So in here, we've been using all these codes just in order to just like merge all of these data all together. So therefore later, when we're doing the regression analysis, we'll be able to just use this data and conduct the research that we want. Yeah. So yes, we might just like skip the part of merging data. So directly jump into the descriptive statistic. In this part, you will be able to have a like brief idea about what kind of variables that we have collected for this research. For example, in here, obviously years and value and temperatures, precipitation, real GDP per capita, nominal GDP, blah, 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 all of this. And let's just continue. So for the part four, that we have some kind of like visualization of the data. So right over here, in here is showing the time series of the average temperature. It's something that really important for this study, that we'll be able to observe what will be the general climate pattern of these four countries. There are Germany, Italy, Japan, and Spain. So let me just say use the above three countries as an example. So basically for Spain, Japan, and Italy, like this, they all share like a general trend. It's like you can see that all over the years, their average temperature has been raising all the time. And I think it's quite interesting as I for this three countries over here, that they share very similar climate pattern altogether. For example, like when the temperature rises, all these three countries, their temperature rises almost at the same time, and also the drops at the same time. It's quite interesting for us. So the next part will be the annual precipitation by country. So in here, I don't really think that we can tell there is any difference among the annual precipitation. They generally like they would just like kind of there isn't any kind of pattern which is observable for us. So in here, it just looks like this. Yeah, and on the other hand, we also like plots. We made this like bar plots based on the production average production. So right over here, you can see all this data. For example, the first one with cereals. The next one will be the milk. We only show the top 10 crops by the average productions over our data sets. For the part five, also made a dashboard, so therefore we can better control what we're doing, things like that. And for the sixth part, I guess will be also the most important part for our study is like the regression analysis. So for this regression analysis, we basically conducted two regression analysis. For the first one will be the OLS regression. In right over here, we'll be able, right over here, what we're doing, we'll be like merging and just trying to clear and process the data, for example, like changing the variable name, things like that. And finally, we have this. So this will be our final, will be our final data frame that used to run the regressions. So right over here, we just like have very similar content as I just introduced to you guys. For example, like total productions, average temperature, average precipitations, things like that. So yes, jump. In here, we even show the correlation matrix of some key variables. So I guess it's quite easy for us to understand what this picture is showing. For example, if we just take a look at the first cube, the y-axis says this is the long total production, and the cube it says is 1, which indicates a perfect correlation. Obviously, it's yes, because if we just find the first term from the from x-axis, it says it is the same variable. So right over here is trying to set the correlation between two different variables right over here. That's what you can get out of these plots. So finally, jump into our result for the OLS regression. So for our OLS regression right over here, I think that it's quite fortunate because we finally get the result that we want. As you can see, the first term, the average temperature, the result is significant right over here, which means that between the log total production and the average temperature, these two shares like a negative correlation, which means that for the temperature, as the temperature grows, rises, then the total production would in fact decrease. I think it is quite intuitive, for this study to say. And we also made the OLS visualization right over here. So for example, the OLS visualization in here, we simply using the average temperature to show what we are doing in here, because you can see that the 95% confidence interval is so narrow, which indicates that the result is in fact super significant. Obviously, if you take a look at other like variables and their coefficients, probably they're not that significant, things like that. But yes, we're quite fortunate that we get the most desirable result right over here. Apart from the OLS, we also conducted two-way fixed effect regression. But however, for this model, we didn't really get the result that we want. In fact, it turns out to be like there is no significance of the result. But however, we also listed this result right over here because I guess that for some groups, if you might want to consider two-way fixed effect regression in the future, that here is the code that you might use for your own study. And I guess, again, it's the visualization. I might just skip. And again, I think the last part will be the scraping. So our group member also in fact, get a government document file from some kind of like from a department in Japan. So here will be the world cloud that we finally get. I think it's quite good for us to see that Japan, or probably based on the case of Japan, and probably we can see that many other governments in the world, they're trying to work on the issues on climate change, stuff like that. For example, in here we can see that like the climate environment protection and the world, like probably the world environment protection, things like that. It's been mentioned a lot of times in the report. So obviously, it's quite happy for us to see that many governments are trying to do this, or at least Japan as a government, Japanese government, they have already been they have a lot of discussion over all these. So I guess finally, that's basically what the cross-national study's been doing. And let me just like hand over the screen to the next team member of us, Yu-san. Yeah.
Hello everyone, this is Yu Kaiji. I would like to introduce the domestic study conducted as part of the AgriEcon project. Our topic is analyzing the relationship between temperature accumulation and green yield per hectare in Northeast China. Northeast China, consisting of Heilongjiang, Jilin, and Liaoning, is one of the country's most important grain-producing regions. As climate change accelerates, agriculture in this area is becoming increasingly vulnerable to temperature fluctuations and weather extremes. The central question we aim to answer was, to what extent does annual temperature variation affect green yield in this region. To investigate this, we adopted a widely used agriculture climatic indicator called degree days or GDD as our key explanatory variable. We then matched it with provincial level yield data to construct a panel dataset and run regression analysis to quantify the relationship between the two. Our study is based on two major data sources. First, I collected climate data using the NASA Power API, retrieving daily maximum and minimum temperatures from 2005 to 2023. I selected three representative cities, Harbin, Changchun, and Shenyang, to represent Heilongjiang, Jilin, and Liaoning province. These cities were chosen for their stable data availability and central location with each province. Second, Yuting manually extract the green yield data from the official website of China's National Bureau of Statistics. This includes annual per hectare yield for major crops such as rice, maize, wheat, and soybeans. The original data was formatted in white tables, so we cleaned and transformed it into a long format structure for further merging. After pre-processing, we construct a three-dimensional panel dataset, the observations by province, year, and the crop indicators, and combine these with calculate annual GDD values. We began our analysis by conducting descriptive statistics and to the provincial level, the results revealed the notable regional differences. The Liaoning had the highest average annual GDD and also the highest average green yield per hectare. Heilongjiang had the lowest GDD and correspondingly lower average yield. However, across all three provinces, yield data showed considerable variation from year to year. This suggests that temperature is not the only influencing factor, and other environmental or management variables may also be at play. To quantitatively assess the relative relationship between GDD and the crop yield, we employed an OLS regression model. We used the natural log of green yield as a dependent variable and included GDD as the main explanatory variables, along with year fixed effects to control for nationwide policy shocks or extreme weather in specific years. The results showed that the coefficient for GDD was positive and significant at the 1% level, indicating that higher cumulative temperatures were generally associated with higher yields per hectare during our study period. Beyond this main model, we also explored several alternative specifications like province fixed effects, crop fixed effects, and separate regressions for individual crops. However, due to the limited sample size, especially after disaggregating by crop or province, many of these extended models lacked significance or robustness. We realized that identifying more nuanced mechanisms would require longer time, serious data, higher frequency observations, and more comprehensive controls. To reinforce our findings, we created scatter plots and regression lines showing the relationship between GDD and the log yield. The points grouped by province generally followed a positive trend, supporting our mean regression result. Thus that our model's R-squared were around 0.42, meaning much of the variation remains unexplained. This highlights that we need to include other variables in future models, such as precipitation, fertilizer use, or crop variety. In conclusion, our study found that within the current climate range, increase in accumulated temperature appears to have a modest positive impact on grain yield in Northeast China. But this effect likely has thresholds. Under extreme heat, the benefits may disappear or reverse. Despite some limitations, our work shows how integrating meteorological and agricultural data can support the regional climate policy and adaptation planning. It also provides a foundation for future machine learning applications and scenario-based year forecasting. Thank you very much for listening.